because the next example is important. So, then start a brand new case. So you have a branch point, and then that kind of integral. I'm saying that is important because we have seen many past com questions using this kind of contour. Make sure you know how to solve problem with this kind of contour. Once once you know that is straightforward. Okay, then this is an example. Wow. 11.8 I is infinity x to the p power okay. And your textbook has the limit of p from 0 to 1. Okay. Obviously, and if p is greater than 1, then you have trouble because it may not converge at a large infinity, right? If x is p is greater than 1, this is linear. Uh, this is quadratic, but then the ratio is less than 1 over x. And that is not convergent at infinity. And but this limit is a little bit over restricted. You just a little thinking, you can see that it's actually minus 1. You can actually extend it to all the way to -1 to 1. But consider this case is okay. You realize that you can extend that, and then you a little bit thinking also will lead you to the fact that I is even function of p. So I minus p same as IP. We'll see that after we get it done. And to show that it's quite trivial, you just do a simple change of variable x to like 1 over y, and everything remains the same except that the power will change to minus p. You do a change of variable, you can show for yourself that that's the case. So it's an even function in p. We'll see that in the final answer. So by the fact that it's even function, you see that also p is you can extend the limit from -1. So when you approach -1, of course you cannot go to -1. Otherwise, the integral will not be convergent at 0. Near 0, with this limit even close to -1, it's still convergent. Right? We'll actually need those kind of facts later. So the idea is, yes, these are not integer. P is not integer, so there's a branch point. Let's figure out the contour. So first you change it to obviously everything changed to Z to CP. This is first is along the y-axis, right? But there's a branch point. You want to go along the y-axis, this integral, right? And now you want to find a contour, a closed contour, and the integral also with this limit it's going to 0 faster than 1 over x. So you can close at large arc. In this case, we want to go all the way from 2 pi because it's 0 anyway. So you go all the way around 2 pi, go back to here, and then you want to make a bench cut. You know, it's branch point. So If you go all the way, you don't want to cut it anywhere because that will cause a branch cut, and that's not good. So in this case, you want to make the branch cut along the wheel axis, and then just going back to 0 along, just slightly below the branch cut. This first integrate slightly above the branch cut along the wheel axis, go around the wheel, go around 2 pi, and then go back to 0 along a little bit below the branch cut. So you don't cause the branch cut. Okay. And to connect that, so you need to go a little circle around it. And this is a circle for a small radius, the radius delta. You go the clockwise direction, right? But whether clockwise and anti-clockwise doesn't matter. We'll later argue that the contribution is 0. Okay, so you have a large circle radius of R, which is 0. That is quite straightforward. So now that's your contour. To make sure you understand this contour, about the branch cut all the way around, back to the branch point, circle around the branch point. Okay, you close the contour. Then you see the singularity inside this loop. So that's a closed loop, right? And the only singularity is the 0 at the x squared plus 1, which has 2 0. One is I, the other one is I. Okay, so encircle two simple poles. So now we can just the singularity at 0 is the branch point, and then we avoid the contour exclude the branch point. We explicitly exclude the branch point. So we are going slightly off 0, so slightly above 0 along x here. So we actually start from 0 to delta to infinity, right? The first one is from delta to infinity, going from theta from 0 to 2 pi. It depends on how you want to cut it. You can define 0 to 2 pi, that's fine, because that is a single branch. And then go the outgoing return path is infinity to delta. And then we go a little circle of radius delta can connect the two straight lines. So you avoid the branch point. You don't go, this contour doesn't include the branch point. The branch point is in the exterior, not the interior of the circle. Well, the c squared, this is small, right? So c squared is 0. And actually, c squared along the path will be delta squared. We'll use the fact that to argue that the little circle will give you 0. The integral along the little circle will be 0. But anyway, the integral is regular because and now we just write down symbolically. So the first part is just what we want, just I. And then this is I infinity. That's I infinity, which we argue that is 0 because if the integral goes to 0 faster than 1 over c. And then going back from 0 to infinity, we need to write. So let's just symbolically write I1. And then this is going down a little circle I sub delta. Okay, and that equals to 2 pi I. And this is still all counterclockwise loop, so that's 2 pi I residue at I residue. Okay, so that's symbolically set that up. We can consider different terms. Consider the delta going around the little curve. So Z is delta E to the beta, right? And consider this integral, this C sub delta is, or I mean, I should say, using the same language, I sub delta. It's going around the loop delta, and dz is I e to the I beta e beta. This is from 2 pi to 0. It doesn't matter. We argue that this is back to 0 anyway. This is delta e to the power p, and then delta square e to the 2 beta. And obviously the delta in the integram doesn't matter because you have 1 to 0. And now altogether you have delta to the 1 plus p power is proportional to delta to the 1 p power. Okay. And as delta goes to 0, it goes to 0. Okay. So that is fine. And then you can see that why is it that as long as p is greater than -1, this is still true. If p is greater than -1, this is still going to 0. So you can still use the same thing. Okay. So I sub delta is 0. Now I sub 1. I don't go too much over that still. A little bit tired. So I sub 1 is, you need to be a little careful now. I sub 1 is Z is we need to choose a symbol. Let's just use R, and then this, to keep this single value, theta is going from 0 to infinity, 0 to 2 pi. That's our choice. So 0 to pi 2 pi. All right. So that doesn't, for x squared term doesn't matter, and the dr is dz is also this d is just dr into the 2 pi I, which is just 1, right? And the tricky one is x to the p, or it becomes c to the p is equals to r to the p power, and e to the p I mean 2 pi I times p. Okay, so that's that part. There's put everything together is this is just dr, 2 pi I is just 1, but then you're integrating from infinity to 0, right? And then you have r to the p power e to the 2 pi I plus p plus x to p, and then we want to take care of dr. Dr just dz is just dr, and then the denominator is just the same, whole square plus 1. Okay, so you recognize that everything is the same as this one except the minus sign, and then this phase factor. So it's equals to minus e to the 2 pi e times 1. I said 1 is this one, right? And now we combine everything. 1 minus e to the 2 pi I p times I is equals to the residue, 2 pi I times the 2 residue. Now I can take some chocolate. So at x, so there are 2 poles. We'll do it one at a time. So residue I is multiplied by x minus I, and leave the x plus I in the denominator. And then you need to be careful now. Don't just use I because you need to keep explicit uh, phase angles. I is just, for our range of theta is e to the I pi to q minus I is actually e to the 3 pi I over q. Right? We need to be a little bit explicit here because we have this x power, x to the p power. So for the I, so you have e to this one into here, I pi over c times p divided by, so this is your x minus I already cancel x. Yeah. Up high. You're right. Just got distracted by the previous example too much. This is I pi. Yeah. Okay, if the denominator is should be fine, you have x plus x minus I cancel. So you have x plus I. So basically adding the two poles. E to the I. I mean, the denominator is not singular, so you can actually use just two I. This is I minus, you have I plus, I mean, z plus I, and then z is unit I, so it's two. Okay, so that's the residue at I, and the residue at minus I is the same because now it's e to the I, a prime to e. Now this is c plus I times c minus I. C plus I cancel because you multiply by the same factor, c minus I, and then I c divided minus I, so it's minus 2. Okay, and now I is equals to, hopefully get everything correct. So you have two I. So everything cancel. You have a pi here, and then you just add the 2 or subtracted it because of minus e divided by e. That you look right. Now you need to see if you can simplify that. At least see if I get it correctly. One minus 2 and the I by p with 2 minus e. Yeah, that this is equation 11.115, and because of the time at 4 minutes, let's see if I can struggle with that. Well, what do you do?
P is a fraction, so we can.
Say that again.
P can be a fraction.
P can be anything, any real number. So we can. Well, we want a general formula.
We can write sign if we take e power I by 2.
Okay. Yeah, you're suggesting taking one factor out. Right?
Yes.
Well, let's see how it works. Taking that out, right? This become 1 minus e to the she have minus 1/2 is just pi, right? And divided by that. That is 1 minus e I pi p times 1 plus e I pi p. At least we can cancel one of these. All right. And then we can multiply this to the denominator. Times e to the minus 1 pi p over q plus e to the e over q. And that add to the just 2 of the cosine. Hopefully that's good. Is it correct?
It will be when the numerator is only the 3 by 3.
In the numerator?
In
Yeah.
that equation, the numerator is for I 3 by 3.
I
3, isn't there a 3?
see.
Yeah.
I take that out. I take that out. Right? You take I pi over 2 out, right? The rest is this plus that is this one. I factor this one out. That's what your suggestion. Right? Like this one is this one. And then I factor this out into 2 factor because this is square. So 1 is a square minus b square. Right? You cancel this one. This one cancel with this one. And this one, divide it in the denominator and multiply with 2 terms, get it this one. And that is 2 cosine of this one. Which is pi over 2 cosine p pi. Yeah, correct. Lucky again. So, I mean, let me make a remark first. To get to the final result, I struggle with it a little bit, but I try to get the final result to make one point that the final result has to be real. Right? After all this complex thing, you better get the real answer. Otherwise, you won't be correct because the original definition is real integral. Everything is real. Okay, now question. Because of the denominator is 0 at I and minus I. You have x squared plus 1, right? Plus I times x minus I. This loop, this little loop. This one, I infinity. Yeah, I infinity is the large circle. The little one, this one I, this one is the original one. It's along this real axis. Here, there. Okay, here, there, and the phase angle along here is 0. So I don't need to worry about x of p. The phase angle is 0. Okay, and then that's our choice. We choose theta from 0 to 2 pi. That's the branch cut. We make a branch cut, then we choose the range of our theta. The theta from 0 to 2 pi. Okay, just about the branch cut is 0. Just below the branch cut is 2 pi. It's important when you return it, there's a phase angle. Yes, still enclosed in 2 residue. You think about this loop. So there's 2 residue, two singularity inside this loop. So we need this residue 3 and include the 2 residue. Okay. No, the I infinity is 0. We make a simple argument that we considered that before. The integral fall off to 0 faster than 1 over x. Then there's the path, the large circle, the contribution will be 0. Because of that r goes to infinity, right? And the total integral goes to 0 along the path. Is that okay? We make the argument a couple of examples. This one, this large circle, we don't actually need to evaluate that. We just need to argue that because the integral fall off fast enough along the path is 0. We make the estimation before. for the general case, you make the estimation that as long as F is for faster than 1 over x, then the contribution from this large circle is 0. Okay?
Yeah, the first term of the equation, I plus I infinity.
Yeah, this one is the original one. I infinity is what the large circle, which we argue to be 0. I sub 1 is what we work out here, is this path going back from infinity to 0 along lower than the branch cut. Okay.
Can you draw the path of the I?
I is from delta to infinity, just above the branch cut. This is the I. There's a branch cut. I go from delta to infinity. Delta will go to 0 later. That's I. That's I. And then go around the big circle is I infinity. Going below the branch cut back to delta is I sub 1. And then going around, connecting the two straight line is this I sub delta, this little circle. And then everything, we exclude the branch point, but we still include the 2 poles inside the loop. Okay, so that's the contour. So this is an important contour, so, at least for the PhD student. Okay, let's stop here. Otherwise, Dr. Charlie will come. All right, stop here.